Hello, happy Friday, everyone. Welcome to the conclusion of EE302 Transient Response Analysis Unit. So I am going to switch over to the PowerPoint slide set, and we'll do a quick recap of where we've been and a preview of where we're going. And then it's time for learning. I just want to recap the fact that you have learned about transient response analysis since probably your second circuits class. Right, in EE211, you talked about when the switch would open and close, and you would analyze what the voltage across the capacitor, say, would be for all time, including the time immediately after the circuit closed. That was transient analysis. All we're doing here is we are expanding that to talk about more systems than just RLC circuits. We're talking about systems in the general sense. And we learned a little bit of new notation for those systems. Where'd it go? There we go. We learned about that we can describe the pole locations of a second order underdamped system in terms of this modified polar coordinates, that is the natural frequency, which is the distance from the origin, and the damping ratio, which is akin to the angle formed with the negative real axis. It's not exactly that because we're taking a cosine in between, but it is 1-to-1 between the angle and the damping ratio. And so once you have all that, then you are ready to start talking about the metrics that this system would exhibit when a step is input to it. And so we derived the expression for the closed form for the step response of this underdamped system. This is all in terms of our new coordinate systems. And from this step response, you could do a bunch of algebra and derive these four equations that give you shortcuts for the four transient metrics that I listed for an underdamped system's step response. So that's all we're talking about here, is that I want you to see that once you know the natural frequency and the damping ratio of a system, you can jump straight from there to this slide here and tell me what the peak time of that system's step response will be. You can tell me what the overshoot of that system's step response will be. Now, that's powerful because before, with your kind of 228 knowledge, what would you have had to do to answer that question? I think you would have had to partial fraction decomposition, inverse Laplace transform to the time domain, get the time domain expression for the response, and then differentiate that, and then set that equal to 0, and then solve for the first time where it peaked, exactly, just to find the peak time. Okay, so what I'm trying to show you is that this isn't new, but it is faster than the way that you would have known how to do this last week or last quarter. Okay, so we left off last time with this example, which was capitalizing on those new shortcuts. But to use the shortcuts, we first had to write the system in its canonical form. That involved using week 1 knowledge to collapse this feedback loop into a single transfer function. And from that transfer function, we could identify the system's natural frequency and damping ratio. Given that damping ratio, we could then calculate what the overshoot would be and vice versa to give us a bound on the damping ratio. And the damping ratio was uniquely determined by K once we have fixed P. Now, there were a lot of assumptions there. In particular, if P is also variable, then K and P both play into the damping ratio, and you could have accomplished this with a combination of Ks and Ps. Okay, so we are going to open today with some example problems, quite a few of them actually. So on this slide, we are given basically the DC motor's transfer function, or the block diagram, and we are trying to answer a couple of questions. First is, what's the settling time when VA has a step input to it? And what's the settling time when the disturbance is a step? So this is our first real, I think, deep thought about what it means for different inputs to be active in a system, right? So this is a 2-input, 1-output system. If you look at the block diagram, there's an input here because this arrow kind of comes from outer space, and there's an arrow here because this signal comes from off the page, if you like. The output is then this one over here. So this I would call a multi-input single output system. Okay, so if we're given all these quantities, in particular Km over Ra is 1, which means we can collapse this block and call it just 1. And we're told that J is 10 and B is 1, so this block is equivalent to 1 over 10s plus 1. And we're also told KB was 1. This is our lucky day. Everything is 1. Okay, so if we want the settling time due to a step in VA, I think the very first step, pardon the pun, is to collapse this block diagram so that we get a single transfer function from VA to omega. Now, let me decompose that sentence that I just said. If I want a transfer function from VA to omega, what does that imply about the disturbance signal? Anyone?
Can you repeat the question?
Yeah, so the question, well, the goal is, if I want to answer question number 1 here, I need the transfer function from VA to omega. And I think that those of you who have tried homework 1 have seen that if there are multiple inputs, it's really hard to collapse a block diagram to have a single block. So the question again is, if I want the transfer function from VA to omega, what does that imply about the disturbance signal, T sub D?
It's 0?
Exactly. If I want the transfer function from VA to omega, that is the exact same statement to, I want the effect of VA on omega. If I want the effect of one input on the output for a linear system, that means I have to set the other inputs to 0. Think of superposition when you were solving circuits. If you wanted the effect of independent voltage source 1 on the output, you would turn all of the other independent sources off, and turning them off meant setting them equal to 0. Okay, so superposition says that if I want the effect of VA on omega, I have to set the other inputs to 0. Which is actually convenient in this case, because when the disturbance signal is 0, this summing junction takes Tm, subtracts 0 from it, and I get TL, which means that Tm and TL are the same, which means the equivalent block diagram is, so VA into the summing junction, Km over Ra is 1, so this is the 1 block. This summing junction means we're adding 0 or subtracting 0, which means, and then this goes into the process block, 1 over 10s plus 1. And this gets fed back with unity gain. What I'm trying to say is that if I have this summing junction, but I'm always summing 0, that's not even a summing junction, is it? Right? Because this is the same idea. If I take the Tm signal and I subtract 0 from it, I get the Tm signal, so there's nothing to do. So, and then this block is unity, so it also doesn't need to be there. And so I get this picture. If I just want the effect of VA on omega, this is the equivalent block diagram, which means I can use my feedback reduction rules to say that the transfer function from VA to omega is top over 1 plus top times bottom. And I think that we're going to get something like this out of that. Okay, so now the question becomes, how do I find the 1% settling time due to a step in VA? If all you knew were the examples from last time, then I think you would be out of luck, because this is not a canonical system. This is not a canonical second order system. It is a first order system. So this does not have natural frequency. this does not have a damping ratio, precisely because this is first, not second order. So I put this example in here just to show you that you can answer these kind of transient questions even in the absence of a canonical transfer function. Okay, so let me go to the next slide. I gave myself a little bit of room here. So we're talking about VA is a step, and we know that the VA to omega transfer function is, if you factor out the 10, you get something like this. So I'm going to try to be real careful here because I've been told in the past that my lowercase s symbol and my number 5 symbol can end up looking really similar. So I will try and make sure that you know that that is an S and that is a 5, because I think that this is a pretty quiet class and I'm not sure that you're going to ask me questions if you have them. So the idea is I want omega in the time domain. If I have omega in the time domain, then I can get its 1% settling time kind of the old-fashioned way. So that means omega of s is our VA times our transfer function. All right. So if I want to break this up into partial fractions, there is going to be a residue on the mode at the origin, and there's going to be a residue on the real mode at 1/5, negative 1/5. And what do you like to do? You like to do cover up here. So to get R0, I cover up this factor and I plug in s equals 0. And I think that gives me R0 is 1/2, if I'm not mistaken. 1/10 divided by 1/5. Is that right? Or is it 2? I think it's 1/2. Yeah. Okay. And then R1, if you do the same practice, you cover up this factor and you plug in s equals negative 1/5 and you get negative 1/2. All right. Okay. So we know these numerators, which I'm going to call residues. Not just me. It's not just me calling them. That's their name. Okay. Weirdos. So let's now take the inverse Laplace transform of this. Now we can get omega of t, which is what, 1/2 times u of t minus 1/2 times e to the minus t on 5 u of t. Okay. So how should we figure the settling time for this? Well, I think that's much easier to do if you can visualize what this graph looks like in your minds, man. So this is, well, its steady state value is 1/2, right? Because when this exponential dies away, the only thing that's left is the first term. And at t equals 0, this is 0. So I think this is our classic charging capacitor shape. And so now the question becomes, let's find the time where this response first or last gets 1% away from its steady state value. So I'm going to exaggerate this drawing. And we need to subtract 1% from 1/2. I say subtract because we know by the shape of this curve that this will enter the bottom tunnel. Like, strictly speaking, there's another line up here at 1% above 1/2, but the response is never going to cross that, so I'm not even considering it. So we need to find the time where omega of t sub 1%, I'm going to call that t sub 1, equals, I think 1% below 0.5 is 0.495. Okay, so then all this is a little bit of algebra. So we get 0.5 times 1 minus e to the minus t1 over 5. And this t1 is clearly in positive time, so I'm not even going to write the step. The step is on, so we don't need to consider it. Okay, so you take some natural logs, you do a little bit of division, and you find that T1 is actually really long. This is about 23 seconds. So it takes this system 23 seconds to settle to within 1% of its steady state value. That's what we just found out. And we did that, I would say, the quote unquote, the old way, right? Going to the time domain, solving for this time, not using any of our new shortcuts. Questions on that?
So just to confirm, the conclusion from this problem would be that our system takes about 23 seconds to reach steady state?
Yeah, where essentially reach steady state means reach within 1% of steady state.
Okay, thank you.
Yeah, good question. Okay, so I'm going to switch back here because the answer to the first question here we just found is about 23 seconds. Okay, so let's consider question 2 on this slide, which is a unit step in T sub D. Again, this means if I want the effect of T sub D on the output, I need to set the other inputs to 0. So this is the exact opposite diagram. This is T sub D is non-zero. And let's see, let's just redraw everything right quick here. This is omega. And now V sub A, we are setting to be the 0 signal. So this is a plus, this is a minus, this is still unity feedback, and this is unity gain. Okay, so this, I'm taking my time here because this has historically proven to be a sticky point for some students. So let's see if I can switch colors. Yeah, there we go. Okay. So what I want to do is I want to rearrange this block diagram so that it's in a shape that I'm more comfortable with. That is, the input is coming in from the left, the output's on the right, and we don't have any of these kind of null summing junctions here. So tell me, what should I replace this section of the block diagram with? What is an equivalent block that I can place there?
You could do 1 minus 1 over the JS plus B block.
1 over?
1 minus.
So
because you have the 0 coming in, so it's just 0 and the negative of the 1 over JS plus B block.
Oh, remember, this is a system. This is the signal omega here.
Right.
So I think you've correctly identified the fact that this signal, the one that I kind of almost completely obliterated, is negative omega. And so I think the answer is much simpler than you were going for. This is just an inversion right there.
Oh, okay.
Yeah. So let's go back to black. Okay, so this red blob is the same as a -1 gain, where the omega signal comes in here and the negative omega signal comes out there. That number 1 block is still a number 1 block, and we get a minus plus here. Again, I'm going slow because I think this is our first, well, this is the first manipulation I've done of these diagrams with you watching. So, okay, but that's the key here, is that when VA is 0, this kind of left-hand summing junction reduces to an inversion on the omega signal. So now, I think, what would I like to do? I would like to show you that this negative signal that I just took all those pains to draw can hop and change that sign there. You see that? It doesn't matter where I invert this signal, whether I invert it in this block or whether I invert it just before it comes into the summing junction, I've still inverted the signal. So let's go back. This is a little cumbersome. But I think what we have, let's go down here. T sub d comes in with a negative sign. And now the other signal comes in also with a negative sign. The output of that summing junction goes into the 1 over 10s plus 1 block. And now everything else is 1 around the loop. Yeah? So I'm doing a lot of drawing and assuming that you're keeping up with me, but if you have questions, please call them out. So we don't have a proper way to reduce this summing junction. We only handled the case when this is a plus and that's a plus or a minus. But I want to show you that if I invert this signal and I invert this signal, that's the same as inverting neither of them, but inverting them here. So what I'm doing is I'm factoring out this -1 from both of the sums, the inputs to the sum, and I'm moving that -1 to here, and then I'm moving it directly to there. Okay, now the diagram is in a form that I have the reduction memorized for. This is forward over 1 minus forward times feedback. And I say, I emphasize the minus there because this is in effect a positive feedback loop. Okay, so this transfer function, omega on T sub d, is forward over 1 minus forward times feedback. All right, and a lot of negative signs hanging out here, but they're all important, right? Like, so if you drop one, you kind of completely get the wrong answer. So I'm trying to go slow. So let's translate this onto the next page where I have some more room here. So what we just showed was that the TD to omega transfer function is -1. Sorry, I'm just going to copy this. I could probably, ooh, hold on, people. I'm going to try something fancy that I think I've seen Dr. Braun do. Hold on. Is this a lasso? Yes. We can do this. Yes. Oh, look at that. Sorry, I'm unreasonably excited about this. Copy that. Paste. Hey. Ooh, that's a lot of nice. Okay, that just made my day. I'm not sure it saved any time. Okay, so what do we got here? Basically, I just want to cancel these negative signs. So I get a, I can also multiply through by the 10s plus 1. So I get a -1 up top, and then I get a 10s plus 1. And then this negative and that sign negative will cancel, plus 1. Hey, look at this. I get a -1 over 10s plus 2. Which is, if you do the same factoring trick I did before, -1/10 over s plus 1/5.
In that first equation, would that be I thought that would be a plus because the summing junction has 2 positive inputs once you.
Yeah, so let's make sure that we remember the rule. So the picture from the slide last week was if there's a G, oh gosh, what's going on? If there's a G there and an H there, and then the key here is that this was a plus and this was a plus or a minus,
Right.
then the rule was forward over 1 minus plus GH. Yeah, so that's the trick, is you got to remember to flip that sign.
Thank you.
Okay, so this is where kind of like coming up for air and not just going full on to these problems without thinking about what you're doing will pay off. Because what we just showed? what did we just show? We just showed that the omega to t sub d transfer function is the negative of the omega of the VA to omega transfer function, which means that if these two are the same signal, i.e. a unit step, then this picture is going to be the flip of the picture I drew on the left, which means T1 here is going to be the same as it was over there. The fact that we inverted the signal doesn't change the time it takes to reach 1%. Okay, so I just saved myself, I don't know, a couple minutes. This is not relevant because you're not taking any exams in my class, but if you were taking exams, it's helpful to save every minute. So let's summarize and say that we did the hard work to do question 1, and then we used question 1 to answer question 2. I think that's the idea. Both of these signals, if they are steps, produce very long-lasting transient effects. That's the one-sentence summary of this slide. So, any questions?
Can you just explain why you set VA to 0 when you're finding TD?
Well, I'm going to point to this argument, which is the converse of what you're asking. When I want the effect of VA, I set TD to 0. And were you comfortable with that?
Yeah.
Okay, so it's just the exact same thing, but I'm switching the labels. So remember in your circuits classes, when you had a circuit with, say, an independent voltage source, and then, say, an independent current source over here, and then blah, 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 what happened, and you wanted to find what's V out. Well, one way to do this was this superposition method, where V out 1 would be if you were to turn the current source off. V out 2 would be if you were to turn the voltage source off and the current source back on. And V out total is the sum of these two. So that was superposition, or how you learn superposition in circuits. Superposition applies to linear systems in general. And so what I'm saying is that the effect of any particular input on the output can be found by setting the other inputs to 0. All right, so I am on the next slide. It looks very similar to the past slide, but that's because we have just taken the system that we were just analyzing. Annotate, spotlight. This, oh boy, that's not what I wanted, is the system from the previous slide. And what we've done here is we've said, well, hypothetically, 23 seconds to recover from a step change is unacceptable. Let's try and speed this system up. One way to do that would be to buy a new motor. Buy a faster motor, right? Throw money at the problem. That should work. Or consider using the same exact motor, right? The same parameters, same J, same B, same KB, yada, 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 and wrap that motor in a feedback loop. That is, sense what the speed is with the tachometer, and then have the motor act on the error signal rather than on the input signal. Okay? So, same exact challenge. Now we want the motor speed to change by a step amount, and we're going to try to find the amount of time it takes to settle to that step change. Okay, so let's see, there's a lot of work to do here, and it's already 40 minutes into the hour. So what I'm going to do is I'm going to use the fact that we already did this subproblem. This, provided T sub D is 0, right? So provided T sub D is 0, this was our first transfer function from before. This is 1 over 10s plus 2. Right? Because this takes the input to this summing junction and converts it to omega. So let's simplify our lives like that. So the new block diagram is the reference signal comes in, and we're told that K sub C is 100 over S plus 2 is our controller block. And that goes into 1 on 10s plus 2. And the feedback gain is 1/10. And because we want a stable system, we're going to hook this up with negative feedback. Okay. So here is where we're actually going to use the contents of this week's unit. Is this will end up being a second order system, and we are able to use our shortcuts on it. So let's go to the next, let's go to a blank piece of paper and work out what the transfer function is. All right, so the R to omega transfer function is, well, it's 10 over s plus 2 times s plus a fifth. Right, I did the same trick where I factored out the 10 from the denominator of the plant block. And 1 plus that, same thing. Times the feedback path, which is also 1/10. Okay, so multiply everything by this second order polynomial, and we get 10 on s plus 2, s plus a fifth, I think plus 1. That works out nicely. Okay, so you FOIL that out, and you will get 10 on s squared plus 2.2s plus 1.4. Hey, all right, now we get to use the stuff that we learned on Wednesday. This is a canonical second order transfer function. It's canonical because there are no s's up top. There's a second order power of s down here. And so that allows me to say, hey, this term, that's omega n squared. So omega n ends up being the square root of that, which is about 1.183. And then this term is the identical to 2 times zeta times omega n. So what I'm doing is I'm just matching this denominator to the canonical denominator from a couple slides ago, i.e. Wednesday. So we know that 2 zeta omega n is 2.2. So if you wanted to solve for zeta, we have all the pieces of the puzzle here. We get zeta is 0.93. And what's even better, we can use our settling time formula. So the T sub 1% settling time is negative of the natural log of 0.01 divided by zeta omega n, which is 1.1. That works out to be about 4.187 seconds. So I don't want to harp on this too much, but the cool thing that just happened is we got what a 5-fold factor of improvement without having to buy a new motor. Right? So what did we do? We had to buy a tachometer, okay, and we had to work out how to take the difference of two signals and then put a filter in. But that's it. Like we put a low-pass filter in, and we had to sum some signals, and we had to buy a tach, but we didn't have to buy a new motor. And the other cool thing that we don't quite know how to do yet, but it is true, is that there's no reason that we know of that KC should be 100, right? If you wanted to have like variable performance, you could have one controller that had a gain of 100, you could have another controller that had a gain of 1,000, and you could work out the transient performance for those. You could have another that had a gain of 10, and these are cheap, right? This would be like a switching between 3 different, I don't know, resistive values. That's way cheaper than buying 3 motors, one for each of these performance requirements. So I I don't know why I'm harping on financial performance. Maybe it's the recession, but it's a good consideration for an engineer to have, at least in the back of their mind. Okay, so we went from 23 seconds to settle to about 4 seconds to settle. So that's pretty good. I do apologize. This is taking a bit longer than I thought. So I am going to leave this as an exercise for the reader. So the last bit of this unit is addressing the very realistic question that is, we just spent 3 hours talking about second order underdamped systems. There are different systems, and you're absolutely right. What happens if we have other stuff? And the answer to that is, you do everything you can to say that you can treat the other stuff like the stuff you know about. Right, so this is akin to why do we learn so much about linear systems? It's because to model a nonlinear system, the first step is to talk about it as a linear system. The same sentence could be said here. What do we do if we have a third order system? Well, you see if you can model it as a second order system. It's the same idea. Make your life simpler by making every problem, well, if all you have is a hammer, everything's a nail. Yeah, that's the idea. We just learned a bunch of stuff about second order hammers, and so we're going to try to make everything into nails. So on the screen here is something that's definitely not a nail on its face. It's not second order. It's in fact third order. And let's assume that the second order part of it is underdamped. So if we were to draw the pole zero diagram here, there are a couple of options. The P value, well, it's got to be real because it's just a single pole. So one option is that the P could be way out there. Another option that we don't know yet, because we don't know P, is that the P could be way in there. I mean, technically speaking, it could be anywhere in here, but these are the two kind of limiting cases. And so what I want to show you before the end of class today is that one of these scenarios is conducive to making a second order approximation, and one of them is not. Okay? So to do that, to make that argument, I need to switch over to MATLAB because it will hasten the derivation of these step responses. So let's see if I can switch to MATLAB. Can I get a thumbs up? Can you see the MATLAB window here? Okay, great.
Yep.
So what I'm going to do is I am going to just pick a couple random values. So I'm going to have a second order natural frequency square root of 2 and a zeta of 0.5. And then I'm going to define the second order system from the previous page in terms of those quantities. And so if I do that, if I execute that block, okay, so here's the second order poles that I showed before. Now I'm going to add to that, well, I mean, by add, I mean multiply. I'm going to multiply that by a third pole. And the pole I'm going to pick is the pole at negative 100. So let's do that. So TP stands for third pole, TO stands for third order. And so now the picture has dramatically changed. So here are the original complex conjugate poles. And here is that third pole hanging out way out here at negative 100. And so what I want to do is I want to use MATLAB to calculate the step responses for both of these signals, both of these systems, the second order system and the third order system. Remember, the second order system has no idea where this third pole is, and the third order system has all three poles active in it. Okay? So before I run this, I want you to stop and think how these two step responses will differ. And if your answer was not by very much, then you and I are on the same page. So these curves are is almost indistinguishable. There is a blue curve and an orange curve here, but they are right on top of each other, so you can't really tell. This is the idea that if I go back to the pole zero diagram, that the further away this third pole is, the faster it decays, the less effect it has on the output. Okay? If you can follow that sentence, then you're good to go on what I'm going to call the dominant pole approximation. So let's change things. Let's move that third pole closer in so that it decays less quickly. So here I've moved the third pole to there, and I'm going to regenerate the step response. Hopefully you can start to see that these curves are starting to separate, but they only separate for the very initial bit of the transient. After here, they overlap again because the exponential contribution of that third pole has decayed. Okay, one more time. Let's move the third pole into 20. So I'm including this pole zero diagram to show you the progression of these third poles that I'm moving in and in and in, and eventually they are going to become too close, is the phrase. And so let's run this simulation. Okay, so now you're starting to see the difference. You're starting to see that the rise time of these two systems is different. The overshoot is nearly identical still, and the settling time is going to be darn close. Okay, so if it were me, I would take this third order system and I would say, I'm going to approximate it by a second order system. Which second order system? This second order system. Because this omega n and this zeta give me pretty good guesses about the peak time, the overshoot, and the settling time. It's not so good for the rise time, but if the rise time is what I needed, then I would do the full third order simulation. Okay, so one more go. Let's move this into 5. Okay, so here is the third pole, and here are our conjugate poles. And let's run the step response. Okay, so here even I, who love to make approximations, have to admit that something's fishy, right? The orange curve is the full third order step response. The blue curve hasn't changed for this entire lesson. The blue curve is the step response of just the second order approximation. The orange curve is now dramatically later in its rise, lower in its peak, longer in its peak time, and its settling time is going to also be appreciably longer. Okay, so I think what we've learned is that, let me see if I can annotate the MATLAB screen. This will be kind of cool. I think it negates it if I say it's cool, right? Then it becomes not cool. What we've learned is that if we have a third pole here, this is okay to approximate by zeta and omega n, i.e. second order. And I think by demonstration, this one was also okay. This one was starting to be a little questionable, but this one, not okay to approximate. Okay, so there has to be, what I'm trying to show you here is that there is a threshold where this is okay and this is not okay. I don't know exactly where the threshold is. In fact, that threshold will probably be context dependent, but there is a threshold. And what we do is we call this the dominant pole ratio threshold. So what we're going to do is we're going to define this quantity psi, and we're going to define it as the real part of the fast pole. And I'm going to put, parentheses s here, because there's actually no reason that this had to be a single real pole. It could have been a pair of complex conjugate poles that were way the hell out here. All right, I think you could run the simulation yourself and you'd see the same kind of results. But the psi ratio is a ratio between the real part of the fast poles and the real part of the slow poles. Again, acknowledging that it could be a slow pole or it could be a pair of slow poles. Okay, so your turn to help me out here. If psi is big or small, those are your options. If psi is big or small, can I make the dominant pole approximation? Can I make the lower order approximation?
Big.
There you go. So your textbook recommends a factor of 10. Okay, I've seen different numbers here, and like I said, the exact number that you put here is going to be context dependent, but that's not the important part of this formula. This alligator is the important part of the formula. Is if this ratio is large, feel free to make what's called the dominant pole approximation. And these are the dominant poles. And these are the non-dominant poles, or the dominated poles. Now note that I've excluded this guy. It's because this pole at -5 didn't fit the approximation very well, so it's neither dominant nor non-dominant. In this situation, when you had a pole here, here, and here, there is no dominant pole approximation to make. You have to treat this as a third order system. I mean, don't let me tell you how to live your lives. You can try and make the approximation, but this this step response here suggests that your approximations are going to be wrong. Your transient metrics are going to be wrong. Questions on this?
What are the fast poles and the slow poles?
Can I open that up to the class? Can anyone answer that question?
The fast poles would be the poles that are more negative and to the left.
Yeah, so that was the topic of yesterday or Wednesday's lecture, is that fast poles are the ones further from the origin. And then conversely, slow poles are the ones close to the origin. Now the scales on the vertical and the horizontal axes are vastly different, right? So this vertical axis runs from plus or minus 1.5, but from 0 to 100. So even this x, let's see if you can, even this pole here is like 20 times further away from the origin than these slow poles. So actually, I think it would be instructive if I go back to, oops, let's clear the screen. Sorry about this. Let's make a new slide. Can I make a new slide? I want to get out of the annotation. There. Okay. Okay, so let's check our understanding. Okay, let's check our understanding. Here's the S-plane. If I have a pole at -5 and a pair of poles at -100, comma, plus or minus 3. You tell me which of these are the fast poles with the parenthesis around the S, and which of these are the slow poles with the parenthesis around the S.
The -100 poles are the fast poles.
Yep, these are still the fast poles. It's not the fact that they're complex. It's the fact that they're further from the origin. So if I wanted to calculate the psi ratio for this particular system, this looks like 100 over 5. Well, the negative of those, but they cancel. So that gives me a ratio of about 20, which means, and if you can answer this question, you followed very well. This third order system is well approximated by second order or first order?
Second order.
Oh, try again.
The dominant pole is the one at the front, so it would be first order.
Good. This is the dominant pole, and this is a first order pole. So this system, its step response, will look like that. There might be some wiggles in here, and those will be due to these guys, but they're going to die out because the time constant for those poles is so much quicker.
Okay, so whatever is on the right of the dominant pole ratio, that is the order, first or second.
Yeah, so the slow poles will dominate. This is actually one of my, and I promise I will end soon, but this is one of my favorite kind of slogans of this course, is that a system is only as fast as its slowest poles. Right, that's kind of what we're learning here. Actually, that's exactly what we're learning here, but never mind that. Okay, good job, people. Sorry for running a little bit over, and sorry for teasing you with that second example problem, but I think we'll close here. Thanks, everyone.
Thanks.